If C is a smooth curve given by either R of t pertaining to a plane or R of t pertaining to space, and you have a closed interval on which they're defined, the arc length of the curve is given by this formula. If you only had the two components from the first case, you would only do these two components in your formula. If you have the third component for space, then you put it in as well. Remember that r prime of t is velocity, the magnitude of which is speed. So you're actually integrating speed over the interval from A to B. Let's look at an example. Find the arc length of r of t equals negative ti plus 2tj plus 6tk over the interval from 0 to 1. Negative t is our x component, 2t is our y component, and 6t is our z component. The derivatives of each of those are negative 1, 2, and 6 respectively. Applying our arc length formula from above, plug in your derivative, square it, the derivative of y squared and the derivative of z squared. 1 plus 4 plus 36, that gives us 41 total under the radical. Square root of 41 is a constant, so when you take the antiderivative, you will put a variable attached to it with multiplication, integrating from 0 to 1, 1 times square root of 41 minus 0 times square root of 41, giving you an arc length of square root of 41 units, which would be somewhere in the neighborhood of 6 something. It'd be between 6 and 7 units long. Another example, find the arc length where you have an x, y, and a z component given over the interval from 0 to pi. I want to do one with trig just so that we're not always stuck with taking derivatives of algebraic terms. Okay, so from the original function, we have the x, y, and z components are 5 sine t, 6t, 5 cosine t. Those derivatives will be 5 cosine t, 6, and negative 5 sine t. Remember, the derivative of cosine is negative sine, so there will be a sign change when you take the derivative of a cosine term. Placing each of these derivatives in the bracket squared, x, y, and z, each one squared and added together. Squaring, we get 25 cosine squared t plus 36. I wrote that in the back, and here's why. That makes 25 sine squared t. I grouped my trig terms together because if I factor out a 25 from Pythagorean identities, I know that goes to 1. 25 plus 36 is 61. And like the last example, the antiderivative of a constant is that constant with a variable. And you sub in pi square root 61 minus 0 square root 61 for an arc length of pi times 61. Pi times square root of 61. Definition, let C be a smooth curve given by R of t, defined on the closed interval from A to B. For any value of t in that closed interval, the arc length function is given by S of t, where S is your arc length, t is the value inside your interval. You will integrate from the beginning of the interval to whatever t value you decide to stop at. And it's still going to be the integral of speed. So that gives us the integral from A to t. You will still use x, y, and z component derivatives in the formula. So the formula is not that much different. Let's look at an example of changing a function into an arc length function. Example, find the arc length function s of t for the line segment given by this function. And this is a vector valued function on a plane, and we're going to keep t from between 0 and 1 inclusive. First thing, let's take our derivative. For the I component, it's -3. For the j component, it's 4. That's your velocity. Now the speed is the magnitude of that. So you have square root of -3 squared plus 4 squared, which is 5 when it's all said and done. S of t equals 0 is our starting number in the interval, so we're going to integrate 0 to t of our magnitude or speed. If you want to look at it that way, it's fine. All right, we have a constant. Now with respect to u, that's going to give us an antiderivative of 5u. Integrating from 0 to t tells us that we have 5t minus 5 times 0, that's 5 times t. So if you need to know the length of an arc for any value from 0 to wherever you stopped, maybe you stop at 3/4, then you'd put a 3/4 here and here. Ultimately, you would plug it into here. 5 times 3/4 would be 15/4, and that would be the length of that arc. So these functions are pretty nice. Now to seal the deal and rewrite your function as an arc length function, S of t is equal to 5t. So I'm going to make a note here, S equals 5t. If you solve for t, that gives you S over 5. Go back to the original function, replace the t's with S over 5. You'll get 3 minus 3 times S over 5i plus 4 times S over 5 for the j component. Now if t goes from 0 to 1, 5 times 0 is 0, 5 times 1 is 5. You have a new interval for S. The magnitude of r of S is 1, and therefore when you integrate that over an interval from a to b, that magnitude is 1, so that gives you an antiderivative of S. Basically, you get the length of the interval. Theorem, if C is a smooth curve given by r of t, then the curvature, K, I think it's also Kappa, don't hold me to that, but the curvature, K, of the curve at t is given by, and there's several formulas for this. I just happened to pick 2, and I'm going to do an example of each one. This one you would use if you had 3 components, because remember, cross product is only good for space. This other one you can use if you separate out the x and the y parts for a plane, much like this one up at the beginning. And it's x derivative times y second derivative plus y prime times x double prime over, now you have to keep this grouped, it's x prime squared plus y prime squared all to the 3/2 power. So they are some pretty wicked formulas. Let's look at some examples. Find the curvature given by this vector valued function. I went ahead and wrote it in shorthand notation, component form. We have 2t, t squared, and -1/3 t cubed. We have 3 components, so from that previous slide we can use the first one, the formula involving cross product. R prime, you take the derivative of each term, you get 2t, and -t squared. The second derivative would be 0, 2, and -2t. Be careful taking the first and second derivative. When we do the cross product of the first and second derivative, remember set up ijk, first derivative, those terms go in the first row, second derivative, those go in the bottom row. We've done these quite a bit, so -4t squared minus -2t squared is -2t squared. For the j component, remember it's -4t minus 0. minus negative 4t is positive. I made a plus sign here so it would help jar your memory, 4t. And then for the k component, we have 4 minus 0, that's 4k. Cleaning this up, we have the cross product of negative 2t squared, 4t, and 4. The magnitude of your cross product, you square each of those three terms, add them together. That's going to give us 4t to the fourth plus 16t squared plus 16. Factor out a 4. And also notice if you factor out a 4, you're going to get t to the fourth plus 4t squared plus 4. That will break down into t squared plus 2 twice. So factor that out, factor a 4 out, and then factor your trinomial. Square root, you get 2t squared plus 2. Speed or magnitude of r prime, we go back up here to r prime. Square each component, add together, and that gives us t to the fourth plus 4t squared plus 4. Again, that will factor as t squared plus 2 twice. Square root of that squared, you just get t squared plus 2. Finally, we can calculate curvature. It's the cross product, which we got. The magnitude of the cross product was 2t squared plus 2 over speed cubed. Don't forget that cubed. It's t squared plus 2 to the third power under here. Slashing out 1 leaves 2 over t squared plus 2 quantity squared for our curvature function. So if you had a particular value of t in mind, you could sub that in and get the curvature of that curve at whatever value of t you needed. Okay, so this gives us the curvature of c at any defined value of t. Let's make a quick note. The magnitude of r prime of t is speed. So that's the change in the arc at any given time. Acceleration, the tangential acceleration, is the second derivative of speed. All right, let's go back up here. We had speed measures at t squared plus 2. If you take the derivative of that speed, you get 2t. This represents the tangential acceleration at any given t. The normal acceleration component is curvature times speed squared. Be very careful. This one is the second derivative. Notice where the 2 is. This one's the first derivative squared. All right, so we got kappa up here. It's 2 over t squared plus 2 squared, so that's k. R prime of t, that magnitude was t squared plus 2. Squared on the outside. This does not mean second derivative. This one does. That just means squared. Cancel both t squared plus 2's and you get 2. Now remember, if you had a curve, let me sketch one real tiny here. Like that. And you pick a point. AT would be, let me change color too. AT would be this one. And then into the curve, just think of it, if you're on the interstate going real fast around a curve, you lean into it, perpendicular, that would be A sub n. Another example, find the curvature K or kappa of the curve RT. Now this one only has 2 components, so we can't use the cross product form. I tried to write the solution up fairly neatly so you could follow along. I'm going to go over it verbally. Our x component is 6 cosine 3 pi t. Our y component is 6 sine 3 pi t. First derivative, we're going to have to use chain rule because our angle isn't just t. So it's going to be negative sine. So let's do it this way. It's going to be negative 6 sine 3 pi over t times the derivative of the inside 3 pi. So that's negative 18 pi sine of 3 pi t. Second derivative of x would be 18 pi cosine 3 pi t times another 3 pi from chain rule. That gives us negative 54 pi squared cosine 3 pi t. For the y component, take the first and second derivatives. You'll find that you get these two as your derivatives. Now this formula you can use for the vector valued functions where you only have two components. First derivative of x times second derivative of y minus first derivative of y times second derivative of x. So it's the absolute value of that product. Carefully plug in x prime times y double prime minus, and I run out of room, these are very long, y prime times x double prime all over x prime squared plus y prime squared all to the 3 halves. You got to really watch your bookkeeping on these. Okay, multiplying these first two, 18 times 54, that's 972 pi cubed sine squared of 3 pi t. That comes from this product. Minus negative 972 pi cubed cosine squared 3 pi over t. Minus a negative, that's why this is a plus, 972 pi cubed cosine squared 3 pi t. In the bottom, when you square this term, you get 324 pi squared sine squared 3 pi t. The second term, y prime, when it's squared, it's 324 pi squared cosine squared 3 pi over t. Don't forget all of it's to the 3 halves in the denominator. If you factor out from the top 972 pi cubed, that will leave you with these two terms. And we know that as long as the angles match, sine squared plus cosine squared equals 1. So this just becomes 972 pi cubed. Same thing in the denominator. I went ahead and factored out a 324 pi squared, and that left sine squared and cosine squared of the same angle. That also goes to 1, leaving 324 pi squared to the 3 halves power. 972 pi cubed over, now remember with 3 halves, it's square root of that cubed. So square root and then cube, square root and then cube. Pi cubes cancel one another. 972 over 5,832 reduces to 1/6. And our last example, find the curvature K of the curve at point P. Now this time, we're not going to let T go around. We're going to pick a point on the curve, eventually find T, and then calculate our curvature. All right, so this one we have an x component, 5t, a y component, 3t squared. Take the first two derivatives of each. Just like our last problem, substitute into this formula very carefully. 5 times 6 is 30, minus 0, still 30. First derivative squared is 25. First derivative of y squared is 6t quantity squared. That's 36t squared. Remember, that's all to the 3/2 power in the bottom. Now, for this particular point, to get our curve at this point, that has to be a -5 and that has to be a +3. At the point -5, 3, t would have to be -1. 5 times -1, 3 times -1 squared is 3. So when t is -1, that curve is at this point. So r, and this is just the ones with the arrows, that's just verification. If you were to actually calculate r of -1, you would get -5i plus 3j, which matches that point. Curvature, when t is -1, we're going to take our curvature function, replace t with -1, 30 over, now that becomes 36, plus 25 is 61, to the 3/2 power. Now, if you get lucky and a number like this, instead of being 61, maybe it's 25, you can square root 25 and then cube it, and you'd have an exact number of 125 under here. The reason I'm not doing that is because square root of 61 is irrational. So if that's the case, you can just leave that bottom number to the 3/2 power. Let me know if you guys have any trouble. These are very meticulous, and you got to be careful with your bookkeeping skills. But reach out by email, in class, or just however you need to contact me, and I hope this helps. Also, check your Google Drive for homework help. I try to write up a lot of solutions to those on there.